of our focus areas at Medicines Discovery Catapult is neuroscience, where there's a significant unmet need across the whole spectrum of CNS disorders. At MDC, we're using a range of human stem cell central nervous system models to model disease, with the goal of producing predictive models with better translation to the clinic. We have a number of technologies that can assay cell profile and cell behaviour. For example, with neurons, we can look at how neurons grow, we can look at their activity and how this changes with disease states or in response to drugs. You can see in this video how human stem cell-derived neurons grow in culture over time. Here, control human neurons are shown, but we can also look at disease models. We can measure neurite outgrowth and branching dynamics in real time while simultaneously looking at cell viability. This is a really useful method since neuronal growth is perturbed in disease states such as neurodegenerative disease or in response to injury or neurotoxic stimuli.
Another assay we've been developing is a neuronal activity assay of human iPSC-derived glutamatergic neurons in co-culture with astrocytes. This is an image of what these co-cultures look like, with the neurons labelled in beta-tubulin in magenta and the astrocytes labelled with GFAP in green. We're able to record the activity of these neuronal systems using calcium imaging-based approaches. The basis of calcium imaging is when neurons fire an action potential to electrically signal to one another, voltage-gated calcium ion channels open and calcium ions flood into the cell. And you can use proteins that fluoresce in the presence of calcium ions as an indirect measure of the action potential and electrical activity. One technology we use is the use of genetically encoded calcium indicators. We can transfect with a lentivirus encoding a protein that fluoresces when calcium ions bind to it, under the control of the neuron-specific promoter synapsin. This allows us to stably visualize the intracellular calcium concentration of each neuron in our cultures over a timescale of weeks. Once we've transfected in the calcium indicator, we can record 3-minute videos up to once a day using an IncuSite SX5 to track changes in neuronal activity over time. So these are 3 videos taken of the exact same cells at 3, 4 and 5 weeks in vitro. And each of the flashes in each video is a human iPSC-derived neuron firing an action potential. Over the first few weeks in culture, the neurons begin to become electrically active. And initially they fire separately from each other, as you can see at 3 weeks in vitro. But over time, they begin to wire up into a mature network and begin to fire together in bursts, as one neuron firing an action potential triggers its neighbours and eventually practically every other neuron in the image to do the same. We're able to record various outputs from this system, such as the number of electrically active neurons in the image, the correlation of firing, the burst rate and the burst strength. We can use this to measure the effects of drugs on how neuronal networks form over time, as well as their electrical properties in vitro in a human model. For example, here we can see the voltage-gated sodium channel blocker tetrodotoxin potently blocking activity in these cultures. Each of these coloured lines is a trace of calcium concentration in one neuron in an image. And you can see that when tetrodotoxin is added, it potently blocks practically every action potential in the dish. This neuronal activity assay is a robust, higher throughput and relatively simple way of measuring the formation of neuronal networks and analysing their electrical properties in human cells in vitro. We're using these techniques to assess the effect of central nervous system therapeutics, as well as using it to understand the phenotypic differences between healthy neurons and those with mutations that lead to neurodegenerative diseases.
We're using these types of assays together with other phenotypic outputs to help innovators understand how their drug or therapy can affect cell behaviour. Our goal is to remove barriers in CNS drug discovery through generation of predictive cell models teamed with a suite of innovative assays.